Okay, we'll keep waiting for people to join. Hopefully my screen should be up though. Sharing. Okay, so we're at the starting time. Maybe I will wait two minutes. Yeah, 2 to 3 minutes. Okay, looks like we have about 20 people, so maybe we could get started now. So today, so this next lab that we're going to do is on feedforward and recurrent language models. And then as long as we have time at the end, we'll just quickly actually show what a state-of-the-art language model looks like. The state-of-the-art model will actually have a different architecture that we'll learn about tomorrow, which is called transformers. So I mean, we won't completely go over how it works, but it should hopefully give you a sense of what a sort of modern large-scale language model can do. So hopefully by the end of today, you'll have seen everything from a very simple engram language model that we developed earlier in the lab, all the way up to something that's sort of state-of-the-art. Okay, so this lab is again under this day 1 language modeling, and it's called this FF RNN LM lab. Okay, and I just made a post on CampusWire. There's actually a small variable naming bug. You could either download the new version of the lab from CampusWire, or I'll just show you how to fix it here. So let's get started. Okay, if you haven't installed these packages before, please uncomment and run these lines. It should install pretty quickly. And then hopefully this shouldn't be required, because we actually have all of the data sets here on the left and the pre-trained models as well on the left. This is just if you accidentally were to delete the data set or delete one of these pre-trained models, and I'll explain what I mean by pre-trained model later. then you could run the cell again to download them from scratch. Okay. So as we saw in the lecture earlier, as well as the lab we just did, the goal is to do this problem that we call language modeling, where our goal is to come up with some probabilistic model of sequences or sentences. So here we're going to use X instead of W in the previous lab. And so here again, we have the same formula where we have the probability of an entire sentence. And then this is called the chain rule of probability. This is equivalent to this product of these different conditional distributions. Okay? And now in this engram language modeling says that here, instead of making the next word be dependent on all of the previous words, in engram language modeling, you only assume that the next word, xt, is dependent on the preceding n-1 words. Okay, so this is the same thing that we just saw in the previous lab as well. Now the difference in this lab is that instead of going through the data set and counting words or counting engrams, instead we're going to have now a neural network solve a classification problem. And the classification problem, this is what we saw in the lecture earlier, is given some history or prefix, in this case 3 different words, I'm going to classify what is the next word. Okay? So again, here we have a 4-gram, and we're going to set up this classification problem, which is given the preceding 3 words, what is the 4th word? So what is the next word? Okay? And so now we're going to consider this model as being something which has some parameters. And that's what this theta means here. And specifically, these parameters are going to define a neural network. So this is a picture which is from the lecture notes. So you can go and you can get more context about this by reading the lecture notes. But here, this is kind of just showing at a high level what this neural network will be doing. We start out with encoding the 3 different input words, right? X1, X2, and X3. And so we start off with a 1-hot encoding of each word. You can also think of this as each word is represented as some integer number. And in that integer location, you're going to have a vector of all zeros and then a 1 in that location. Then that 1 of k coding is going to change into a word embedding here. Then we're going to have this projection layer, and we're going to take a softmax. So we'll see this all in detail and in code below. So if that was too quick, we'll hopefully see this again. But essentially, your input to your network is going to be 3 different words. And then the output here is going to be a probability distribution over what is the next word. So that's going to be the goal of this first part of the lab. Okay. So again, we're going to use the same, it's called persona chat, the same chat-based data set. So here is code for loading the data set. And again, for things like this, for things like data loading, I'm not going to go into the details of how everything's implemented. But if you want, all of the code is available here. So in this case, we're loading this data file as this data utils, and then just calling these different functions. So if you want, you can look at how these different things are implemented, but I'll explain kind of after you call these different functions, what we get at the end. And then afterwards, just due to time limits, you can go and look at how things like this are implemented. Okay, so one thing that we do is to create this dictionary class. You could also call this vocabulary if you wanted, but we'll call it dictionary. And what the dictionary does is it takes different sequences in the data set and it turns them into integers. So let me just show you an example. So here we're taking an example from the data set. That's what this is doing. And our data set has 3 different splits. So this is kind of a common thing that you do in machine learning, is to separate the data set into training, valid, and test splits. And so here we're taking, for the training split, just one example, and then we're encoding it into some sequence. And what does that mean? I think it's best to just look at this example. Here is the example from the data set, and you can see that it's text, right? Now, what this dictionary is doing is it's taking every word and it's converting it into its corresponding integer index, right? So it looks like the word I is represented by the number 4, and it looks like the word allergies is represented by the number 11. Okay, and so this is just because when we go to implement a neural network, you can't really give it words. You have to give it some number, which is equivalent to the word. And if you're wondering exactly where these numbers come from, well, that comes from creating this dictionary. Okay? So you could take a look at this implementation here. But at the end of the day, the important thing is that we go from kind of text here to these numbers. Okay. So now that we have our data set represented as these numbers, which you could call vocab indices or token IDs, the next step is going to turn the sequence into engrams. So let's just run this and take a look at the output, and then we could understand what's going on. Okay, so here we're saying that we want to have 5 grams, and a 5 gram, again, is just going to be a sequence of 5 tokens or 5 words. Now, these 2 lines here are tokenizing the data set, which means converting all of the words into these numbers, and then slicing the sequences into these different engrams. Okay, and now here we're looping through, and we're looking at 10 different examples. Example engrams. So we're going through this loop and saying, okay, each engram that we just created, decode it into words and print it out. So in summary, here we see what our new data set looks like when it's separated into engrams. Our first example is this, so 4 beginning of sentence tokens, and then I. And then the next engram in the data set is 3 beginning of sentence tokens, and then I am, and so on. So you can see how the sequence got turned into, 10 different 5 grams. Okay. Okay, so this is still data processing. There's one last step, which is, I'm not sure how familiar you are with PyTorch, but typically when you train a neural network using this PyTorch library, you can use these existing utilities for loading data. So here we're going to use something called the data loader. And here we're just going through each data set that we created above. And we're creating a data loader for it. So again, unfortunately, I can't go into all the details of what's happening here, but there's essentially 2 steps. One is to create this engram dataset class, and that's a PyTorch dataset. And then you give the PyTorch dataset to this data loader class. And this will allow us to easily get these different batches to train the neural network. So here, if we run this, maybe it takes a few seconds, and it's creating these 3 different data sets. So training split, a test set, a test split, and a valid split. So if we look at now in data loaders, you have a training data loader, valid, and test. Okay. So again, just to quickly review, we start with some raw text. We tokenize it to be into these integer indices. We slice it into engrams, since we're using an engram model. And then we create this PyTorch data loader. Okay, now the next step is to define the actual neural network. So the first question is, in this pre-processing, we said that our text is represented as an integer. But what we want to do is transform it into a vector. This is commonly called a word embedding. And so the way we're going to do that, we're going to change this integer token ID into a vector that's in RD, d-dimensional vector, and we're going to use this PyTorch embedding layer to do that. So here we're importing it. If you want, I just want to show you this trick. In the notebook, if you put a function or class name and do 2 question marks, then you can actually look up very detailed documentation for it. So again, we're not going to have time right now to read through all this, but if you ever get confused, PyTorch has very good documentation, and you can really easily access it here in a notebook. And you can actually look, it's printing out the source code too, if you're really curious about how it's working. So again, our goal is to convert these integers into vectors. So we're going to create an embedding layer, and we're going to say here that we want 1 embedding for each item in the dictionary or in the vocabulary. And then we're going to set the dimension to be 16. So the 16 here is this D in this mathematical view of it. And then this is kind of a detail that you have to know about. but we'll actually discuss it below, and it's not relevant for the engram model. But essentially, when you have sequences of different lengths, you have to add in these padding tokens, and you want those to get an embedding of equal to 0. But actually, we'll go over this below in the recurrent language model, and you don't have to worry about it right now. So now if we look at, we call this embedding a lookup table, and if you look at its dimensions, it's going to be the size of this vocabulary, which is 20,000, times 16, which is this dimension that we found. Okay, and now let's take a look, let's have an example of what this embedding or lookup table is doing. So here we're going to take two words, hello and world, and we're going to encode them into integers. So if we look at this printout here, those hello and world corresponds to 179 and 373. Now if we look up in our embedding table, what are those two numbers? Okay. We get some vectors called input embedded. And you can see that you get two different vectors, and they're each of size 16, right? Because we looked up two different words. And then here we're printing out one of the embeddings. So out of this data structure of size 1 to 16, we're accessing 0, 0. And that gives us this embedding for hello. And so here you can kind of see the whole story, that we're going from a word to some vocab index or dictionary ID, and then to a vector. And it's through this embedding layer that we're doing that. Okay. And so now we're going to be able to use this as input to our neural network. As our neural network will kind of expect vectors so that the vectors can get transformed. And so how will they get transformed? Well, the neural network is going to have three different components. So the first is this embedding layer. That'll take us from a vocab ID to a vector in RD, such as this one. Then we're going to have this hidden layer, and the hidden layer takes n different d-dimensional vectors and maps it to another vector, which is in some other dimension, which we'll call h. Okay, so why do we have this n here? Well, if you think back to the lecture, when we were talking about the engram language models, we talked about this concatenation. And someone actually asked, why do we use concatenation? So here, this is just showing the concatenation. It's saying that we're going to have n different input words, and we're just going to concatenate all of their embeddings as input to this hidden layer. Okay, and then after applying this hidden layer, we're going to have something which we call the projection layer. And projection layer just goes from this vector to something that's equal to the size of the vocabulary. And yeah, sorry, I didn't mention that. So the embedding layer itself has parameters, so you consider it to be part of the network. And so over the course of learning, the representation of this word hello will actually be changing, since the parameters of this neural network, which includes the embedding, will be changing. Okay, so then in this final layer, we have this projection. And the reason we have the size of the vocabulary is that we apply the softmax operation, and that gives us some probability distribution over the next word. So if you view it as a kind of formula, this is our neural network here. Embedding, hidden, projection, and then softmax. Okay, so then how do we implement this? Well, here's a class which we're implementing with PyTorch, and we're going to have this lookup, this embedding, which we'll call lookup. Then we'll just have this single hidden layer, and then we'll have a projection layer. And when I say layer here, there's this pre-built class in PyTorch, which is a linear layer. Right, so a linear layer will give you a weight matrix, you call it W, as well as a bias term. And so here we're just specifying what are the dimensions of this linear layer. And if you want to make the connection between this and this kind of notation view here, this input size and this hidden size is basically saying, what are these two different dimensions here? Okay. So now that we've defined the different elements of this neural network, now we have to define the forward pass of the network. And this says, given some input, what is the sequence of operations that you do in order to get your output? And here, we're kind of implementing what we've written above, where we look up the embedding for the input. This is flattening it. And that will have the effect of doing this sort of concatenation. Then we're applying the hidden layer. I guess here we have this tangent activation function, and then we're applying this projection layer. Okay. And then it turns out, this is maybe tricky if you haven't used the PyTorch before. It turns out that in this forward function, we aren't going to take the softmax because the loss function that we'll use will actually do that for us. So here we're just returning the output of this projection layer, and this is typically called logits. Okay, so that's our neural network. Okay, please explain, the softmax part. Yeah, so, okay, so if you look at this operation, what we're actually implementing in this forward function is actually everything up through here. And the reason is, I mean, you could, if you want, implement the softmax, but the way it's implemented here, what we're going to do is, let me skip ahead of it. We're going to use this criterion here, which is the loss function, called cross-entropy loss. And cross-entropy loss actually takes a logs softmax internally. So it is kind of tricky if you haven't seen that before, but that's why you don't see softmax here, because this criterion is going to actually have the softmax internally. Okay. So now here, what we're going to do is, okay, so the tangent activation function, you could, there's other common activation functions like ReLU or sigmoid. For the, I mean, maybe we could go into more detail, but for here, you could just think of this as being some arbitrary decision. Okay, now here, we're going to have the, okay, so here, we're going to imagine we're training from scratch. So we're going to put load pre-trains as false. This is setting up the GPUs. This is loading a pre-trained model. And here is training from scratch. So here we're just specifying what are these different dimensions. So we want our embedding size to be 256. We're going to have an engram order of 4 and a hidden size of 512. And you can see again here, we have the embedding size multiplied by the engram order, which is what we had written above here. Okay, now here, if you came to the lab, you get this, you get to see how to get this to work. So this variable name should actually be called dictionary. Let's see. Oh, I didn't run the cell. Okay, so this is just specifying the options, and then we set up this loss function, and then we set up an optimizer. So here we're saying, we're specifying which parameters we want to change during the optimization process, and then we're using this SGD optimizer. And again, if you want, you could do this. You could look up any of these terms, for instance, like this, right in the notebook to look up more details. And so here, you see this thing about it takes a log softmax. But yeah, just in terms of time, I should probably keep moving. But the major parts are define your model, define your loss function, and then define your optimizer. Okay, so now we have a training loop, and this will be a pretty common theme that we'll see again in the course. So this one time I'll go through the different steps, and then actually in the future, the training loops should be fairly similar, so we might go a bit quicker in the future. So here we have different epochs, and an epoch means you're iterating over the entire data set. Okay, so this is for one iteration of the data set. We're going to form these different batches, and that's where we use this data loader. So the data loader gives us an input batch and some target batch. And then we put it on the device we're using, which is the GPU. Then this is just a PyTorch implementation thing that you have to set this optimizer's gradients to be 0. And that'll clear out, for instance, gradients that are stored from previous times you've used it. Okay, so now you do a forward pass, which is just applying the input, and there you get the logits. So this is to make sure that the sizes are matching up. And then here we're just, for logging purposes, summing the loss items. Okay, Now here, again, we actually don't have to worry about this padding until the RNN section, but just to keep the training loop the same, what we want to do is find the average loss over all of the time steps that we're training with. And we want to average over the number of tokens, but we want to exclude these padding tokens. So here we're just finding this normalizer, and then we divide the total loss by this normalizer and do a backward pass. Then after that, we take this optimizer step, and that's one round of training. Okay. So then similarly for validation, we're going to loop through some validation data set. And here, we don't have an optimizer because we're just doing validation. And we do a forward pass and get the loss and record it. And again, we're doing this normalization. I'll go over this padding when we get to the RNN section. So that was kind of quick, but hopefully there's at least comments for the different steps. And you could take a look at this training loop and validation loop, which is a pretty common setup for these models. And so if we run this, we can see that, so here we have this printout, and it's printing out every 100 steps. And you can see that the training loss is decreasing. Okay. So then what will happen is every time one of these epochs ends, so every time you go through the data set the entire time, you run this validation. And then at the end, we pick the model which has the best performance in the validation set. Okay, so I'm not going to let the whole thing train here. Instead, we actually have a pre-trained model that you can use. So this model, we sort of let the training run all the way and then saved it in this file. And you can load it by just setting this to true. Okay, so now if I run this, now it'll skip this training loop. And we could take a look at what the training process looked like for this model. So here we're looking at the training loss and the validation loss as the number of epochs is increasing. So this is like the number of rounds that we go through the data set. And so you can see that the training loss here is decreasing, and the validation loss is decreasing as well. But then here, if you look closely, it actually increases. So on this plot, we would actually pick the model not based on the training loss, but based on its performance on the held out validation set. So we would actually pick this point here. Okay. So this is what it might look like. It might look slightly different if you were to run all of this, but it should look like something similar to this. Okay, so this point is too high. Yeah, so there is this gap between validation and training. I guess maybe I should have shown even the curve even longer. What you would see is that this curve starts increasing. And so at least with these hyperparameters and this model and this data, that's sort of the best that we can do in this case. And so you sort of pick the best model that you can get. Of course, ideally, we would want it to be lower, but it's sort of relative. So now, in order to compare these different models, we're again going to use this idea of perplexity. Okay, so here's the same formula that we saw before. So maybe I won't go through it in detail, just out of time. But we're going to compute the same quantity that we did in the previous lab for this neural engram model. So that's what this code is doing here. And you can see here that the perplexity is somewhere between 45 and 50. Okay, so you can get some sense of the performance there. And actually, it turns out that this is actually kind of similar to the KenLM performance, at least for this model setting. But in theory, especially on a larger data set and with more hyperparameter selection, you should be able to get the neural model to have even lower perplexity potentially. But again, we are using this engram based model, so you can only go so low. Okay, so in terms of the engram model, that's the whole setup in terms of training. Another thing we can do is to look at these different conditional probabilities. So the same thing that we did in the previous lab with the count-based models. Again, I think just due to time, I'm not going to go through every line of the code here, but if you want to understand what this is doing, it's essentially taking this trained model and it's computing this conditional distribution. So given the preceding 4 words, what is the distribution over the next word? And so here's an example. If you have these 4 words here as a prefix, we're going to find what is the distribution over the next word. And then we're going to specifically look at what is the probability of certain words. So, well, let's just look at the result. So, for example, here we have this prefix, BOS, I have a, and then we're looking at what is the probability of dog being the next word. So that's why dog is right here. And it's doing that by calling this function. And so here you can see that the model has learned that the probability of dog is higher than the probability of zebra. And that's actually higher than the probability of donut. And then this is a type of dinosaur. So it turns out that, oh, well, actually, the probability of velociraptor that will be lower than probability of having a donut. So you can get some intuition that this model has learned a somewhat sensible ordering for these different words, given that this was a data set about things that people talk about. So you might expect that people talk about having a dog a bit more than having some sort of dinosaur. Now here, this is doing something similar. Again, unfortunately, we can't explain like everything of how this is being implemented. But this is saying for a given prefix, what are the most probable words to come next? So here we're taking the softmax of the logits, and then we're looking at what are the top k, in this case, top 10, most probable next words. and then we're printing that out. And so you can see that actually dog, according to the model, is the most probable next word, followed by cat, and so on. And so here, for example, you don't see donut or velociraptor because those aren't in the top 10 most probable next words. Okay. So now we're going to move on to the recurrent language models. And the difference here is that, so we're again modeling this joint distribution of a sequence, except now we're no longer going to have this n-gram assumption. Now we're going to allow to model the probability of the next token using the full history, which we'll call x less than t. And in particular, the way we're going to do that is to use this recurrent neural network function, which has this hidden state, h, and at each time step, the recurrent neural network receives the previous token as well as this hidden state and produces a new hidden state. Then you have a similar thing here. This could be called this projection layer, which is transforming this into something that's the size of the vocab. And then you're taking a softmax to get the distribution. Visually, this is how it's one way of visualizing it, where at each time step, you have this RNN cell, which is receiving the previous hidden state and the previous word, producing some distribution, and then it's producing the next hidden state for the next time step. Okay. Now there's different ways of implementing this f of theta. Here's a simple formulation, which is the one that we'll use below. And there's also more complicated ones, or not complicated, but more expressive ones. And I think we'll discuss motivations for those tomorrow, actually. I guess I have to go a bit fast in this part, just due to time. So when we talk about the implementation, you could look at this PyTorch RNN cell, where here we're defining the embedding dimension and the hidden dimension, and then defining this cell, which you could think of as being this box here. Okay. Now these three lines are kind of showing this process here, or this equation here. What we're doing is we're creating some initial hidden state, which is a vector. Then we're creating some random input vector. So this is going to be the size of our embedding dim, the embedding dimension, and it's going to be some random input. Then we're going to apply the RNN cell to the input and the hidden state, and we're going to get a new hidden state. So you can see that the state changed from 0 to this. And you could imagine if you apply this over an entire sequence, then it's going to kind of keep evolving this hidden state over time. So that's kind of showing what this diagram is showing up here. Okay, now, it turns out that in PyTorch, there's a additional kind of building block on top of this RNN cell, and it's called RNN. And RNN just allows you to have more flexibility in terms of you could define a multi-layer RNN, and it has kind of convenient application of multiple time steps at once. So again, here's the documentation for both of those if you are interested. in more detail, but let's take a look at how it's used here. So here we're defining our model again, and it actually looks very similar to the engram model above, except the one difference is that now instead of this hidden linear layer, we now have this RNN. Okay, so now here we define some input, hidden, and number of layers, as well as this dropout. And then again, we have projection and lookup. And so, like I was saying before, the nice thing about this RNN class is that it kind of hides a lot of the complexity, and that you can actually just view everything as doing this one operation here, where you're taking your embeddings and you're getting some output as well as some hidden, and then you compute your logits. Okay, so now again, we're going to go through the process. So we defined our model. Now we define our data set. So we'll let this load. And now the difference with the engram model is that our input isn't an engram anymore. Now it's a full sequence. And then the output is actually still similar in that we're trying to predict the next token. So what it'll look like is this. The input looks like this, where you start with beginning of sentence and go towards the period. And then the output at each time step is going to be the next word. So when you view it as a sequence, it's kind of shifting the sequence. So at this first time step, the output is going to be I, which is actually the next item in the sequence. At this time step, the output is am, which is the next thing in the sequence, and so on. So at this last time step, the target will be to predict end of sentence given this period and everything before it. Okay, so again, here we're going to create this data loader, and it's very similar. The only difference is this idea of padding. And so what is padding? So padding says that if we have a batch of multiple sequences, the sequence length might differ. So in this case, for instance, this sentence is, I should have printed out the length, but this sentence is a different length than this one. But we want all of the sequences in the batch to be of the same length, in this case 21. So to do that, we just add these additional padding tokens here. So now every sequence in this batch is of length 21. And then what we saw before is that you actually want to ignore the embeddings for the padding, as well as ignore the loss at those time steps. And the reason is that for different ways of forming the batch, you might have different amounts of padding, and you don't want that to affect the training. And then also at test time, you might have a different amount of padding. So you just don't want that to affect the actual model itself. So here, again, we won't have time to step through each line, but you can kind of see, just looking at it roughly, that this looks very similar to what we did before in terms of initializing the model, making this loss function, and making the optimizer. Here we have an option to load the pre-trained model or to train from scratch. Now the options might just be a bit different. And here we're explicitly telling our loss function to ignore padding indices. So maybe you could just note this down as being important for the RNN model. So again, let's try training from scratch. And now here, this loop should be very similar to what you saw before. Except for we have to fix this bug here. So instead of this persona loaders, this should actually be called data loaders. Okay, so here, this should be called data loaders. And then here, again, this should be called dictionary. So on CampusWire, I've posted the fixed version, but if you want, you could fix these naming bugs here right now. Okay. So let's see. So you'll have to take my word for it that this is very similar, or actually pretty close to identical to what we did before. And that's why we had this in before, because now this is actually relevant here, where you only want to count the loss at non-padding indices. Okay. So let me, it looks like we have 5 to 10 minutes, so let me just speed up a bit. So again, we see a similar thing with the evaluation, where we have the validation loss and the training loss. This is looking at the pre-trained model. And we can again measure the perplexity. Okay, so it looks like, I mean, we could really print out the exact number. It looks like this is closer to 40, or maybe even a bit below 40, which at least shows that with this model, we were able to beat the engram-based model that we saw before. Again, we can do these conditional probability queries where you see something similar here. Now, the difference here is that with the RNN, you're not restricted by the length. So here I have a pet. You could add in as long of a context as you want. You're not restricted by this engram length. So something like that. I have a pet dog and a dog. And here, this is showing the same thing as before. Now, the one difference, or the one new part is this idea of sampling. So given one of these models, we can actually generate a sentence from the model by sampling from its distribution. And the way that we're going to do that is we're going to start with a blank token, a beginning of sentence token. And then until we generate this end of sentence token, we're going to form this conditional distribution and then draw a sample from it. And this is just a categorical distribution. And then we're going to add that sample to the context and then repeat the loop. So we're going to keep doing a forward pass through the network, getting a new word, and repeating the process. So we're going to go into more details on this in other lectures and labs, but I thought I would, without going into maybe all the details of the implementation, just show you the sampling in this lab so that you can get an idea of generation from this model. So here's some actual sentences that this model has generated. For example, I have a Honda Civic. I play with my C job. I have a unhappy, teeth blonde. I play in the city, but I do not games. I have a big sleeve and then rock places. So you can see that this model isn't definitely isn't perfect. You can also use something called temperature, which kind of sharpens the distribution. And in that case, you could see that it maybe looks more reasonable. But we'll actually talk about this later, that this is kind of a trick that you use to change the model's distribution. Minutes, but in those 2 minutes, I wanted to show you what you could do with a sort of state-of-the-art model. So this model is called GPT-2, and it's a large-scale model with something like hundreds of millions of parameters, and it was trained on a large-scale data set. So the training actually took around, I think, a month, and then the authors of this work made the pre-trained model available. And then another group made an open source implementation of it through this library called Transformers. So it's really nice. You can actually install this library, get the same trained weights, and you don't have to train it for a month yourself. And then you can use a very powerful language model. And you can see here that just loading the model and this tokenizer is just a few lines of code. And then we're going to do the same thing that we did above with this RNN, which is to draw different samples from this model. So here we're going to start with this prefix, my favorite food is, and then we're going to just generate by sampling different samples from the model. And you can see that unlike above where these sentences were kind of not the greatest, here this large-scale model sentence, see my full screen because of the chat and so on. But for instance here, my favorite food is from this little place. It is located in the middle of the main street for those that have been missing for years. I can't see this part of my screen because it's blocked. So on, they do a fantastic job of giving you that delicious chicken. So it's a pretty creative text. Down here we have, my favorite food is the pork shoulder. They have a good variety and I prefer to mix both. And these are just being generated by this language model. So, and if you want, you could change this to something else. My favorite course in school. Of course, it should say natural language processing, right? Okay, my favorite course in school is reading. It gives you the knowledge and skills you need to be successful in life. So you can see that it is able to generate this kind of sometimes funny, sometimes convincing text. And then later, in a couple days, we'll actually talk about why this model is not all the way here yet. We'll actually talk about some common errors that these models make. So you should always have in your mind about this is very impressive, these samples that the model generates, but you should also have in your mind of like, okay, what are the downsides of this? Where are the failure points of this model? And then how can we fix those? So I apologize about the speed. Had to go kind of quick on this, but hopefully you got an overview of these neural engram language models, the recurrent models, as well as at least what the outputs of a state-of-the-art model might look like. And really, I'd encourage you to take a, we'll be using this later in the course, but this is a great library where you can really quickly use these pre-trained models. Okay, so that's it for the lab. If you want to stay on for a couple minutes, we have to remember to turn off the GCP instances. So let's do that here. Let's see, off the top of my head, I guess Google Cloud Platform. Okay, so I just typed Google, so cloud.google.com. Now go to console. Okay. And now if you go to, I think it's compute engine and VM instances. Okay, so just to show that again, compute engine, VM instances. Now here's my running machine. And if you wanted to keep, going through the lab or playing around with the models, you don't have to necessarily do this right now. You just want to make sure to do it so that at some point so that you don't keep getting charged. So, okay, so now I selected the machine and I would press this stop right here. So let me actually turn mine off. Okay, so here it's stopping it, and that should be all you need to do. Shreyas, let me know if you need to do something else. But that should stop your instance. So here you can see it's still working. Okay. Thanks for your attention, and please let us know any questions in the campus wire. Thanks. And we'll see you tomorrow.